Chapter 2, Summarizing and Graphing Data. Section 2.2, Frequency Distributions. Frequency distributions are a way of summarizing data. Consider this table of data. With a quick glance, it is difficult to tell if a lot of the women surveyed have pulse rates in the 70s, 80s, 90s, 100s, etc. A frequency distribution is a way of grouping data into more manageable categories so that basic information can be read from it quickly. Here's one example of a frequency distribution related to the pulse rate data above. We simply count up the number of pulse rates that are between 60 and 69, and that count goes directly in the frequency column. In other words, 12 of the pulse rates are between 60 and 69, 14 of the numbers are between 70 and 79, etc. Zooming in on one of those first two rows, our frequency distribution, we define a couple terms. The left column consists of what we call classes. If the class consists of a range, such as in our example, we call the first number a lower class limit, and the second number is an upper class limit. The class boundary is a number between an upper class limit and lower class limit of consecutive classes. For example, 69.5 would be a class boundary between the first and second classes. The class midpoint would be the number in the middle of a class. So, for example, 64.5 would be the class midpoint of the first class. Class width is a slightly less intuitive. It is the difference between lower class limits of consecutive classes. So consider the first and second class. The first class goes from 60 to 69, the second class goes from 70 to 79. If we subtract 70 minus 60, we get 10. So in this case, our class width is 10. The class width should be the same for each class in any frequency distribution. In other words, all our classes in this example have a class width of 10. So how do we construct a frequency distribution? Suppose we are given a table of some data. In this class, in our class, we will usually be told how many classes to use. However, there are techniques available to determine the ideal number of classes to use in any frequency distribution. In this example, we will construct a frequency distribution with 4 classes. The first thing we must do is calculate the class width. To do this, we start by finding the difference between the maximum value in our data and the minimum value in our data. Then we divide by the number of classes we were told to use. In our case, we come to about 5. If this calculation ever results in a decimal, you will round up to the nearest whole number. The second step is to use the minimum value as the lower class limit of the very first class. So in our case, we start with 60. Third, to get subsequent lower class limits, add the class width, which we just calculated in step 1. 60, 65, 70, and 75. Step 4, identify the upper class limit for each class. If any of our data has 1 decimal, our upper class limit should have 1 decimal. If our data has 2 decimals, our upper class limit should have 2 decimals, etc. Notice in this example, none of our data has any decimals, so my upper class limits are going to be the next number closest to the next lower class limit. For example, for my first class, I go as high as 64, but I don't need to go as high as 64.9 because none of my data has any decimals. Lastly, step 5, count up how much of the data belongs to each class. So, since I see two numbers in our data that are between 60 and 64, I put a 2 in the frequency column next to 60 to 64. Continuing this process gives me 3 pieces of data that go between 65 and 69, 4 between 70 and 74, and 1 between 75 and 79. We have the related concept of a relative frequency distribution. On the left is a frequency distribution that we just talked about. On the right, I will compute the relative frequency distribution. To calculate the relative frequency distribution, we first have to add up all the frequencies in our column of our frequency distribution. So in our case, 2 plus 3 plus 4 plus 1 is 10. In our relative frequency distribution on the right, instead of the number of times we have data between 60 and 64, we instead write down the percent of all our data that belongs in each class. In this example, we would say 20% of our data belongs in the first class. But we could also use a decimal and say that 0.2 of our data belongs in the first class. We get 0.2 by dividing the frequency, 2, by the total of all frequencies, in our case, 10. Moving ahead, we see that 30%, or 0.3, belongs in the second class, 40%, or 0.4, belongs in the third class, and 10%, or 0.1, belongs in the fourth class. This, we have circled our relative frequency distribution. Another type of frequency distribution is called a cumulative frequency distribution. In this type, instead of our class being a range between two numbers, we consider classes as being less than a number. So looking at our data, we consider how many data points are less than 65. We can get this information from our original frequency distribution. Since we know that only 2 of our data are between 60 and 64, then we know that 2 of our data are below 65. For the next class, we consider how many of our data are less than 70. This includes the ones that are between 65 and 69, but also the ones already counted in the first class. So we say 5 of the data are below 70. That is 3 of the data and 2 of the data give us 5. Continuing on, we see that 9 of our data are below 75 and 10 of our data are below 80. So, in effect, we are taking our frequency distribution that we originally had, but just adding each row to the previous row. We tend to see certain patterns in frequency distributions emerge more often than others. One such pattern would be the idea of a normal frequency distribution. This concept of normal will come up many times in this course and be an important part. The general idea at this point is that frequencies in lower class limits are low, then the frequencies get larger, but then taper off again to being low. This would be an example of a normal frequency distribution in a strict interpretation. The frequency starts at 10, grows to 15, grows to 27, then begins to taper off to 22, 13, 8. Section 2.3 Histograms. A histogram is a graph consisting of bars of equal width drawn adjacent to each other. The height of each bar represents a frequency. The width of each bar corresponds to a class width of a frequency distribution. Here is an example of a histogram summarizing a sample of black cherry trees. We see from this histogram that 3 trees are between 60 and 65, 3 trees are between 65 and 70 inches, 8 trees are between 70 and 75 inches. Notice that there may be some ambiguity. For example, what if we had a tree that was exactly 65 inches? Does it go in the 60 to 65 category or the 65 to 70 inch category? In actuality, we won't have such overlap because the values on the horizontal x-axis correspond to the lower class limits from a frequency distribution. Here is another larger version of a histogram. As histograms get larger and as more data is summarized, a histogram can begin to take a shape that can tell us a lot about the original data. If a histogram corresponds to a frequency distribution, a relative frequency histogram corresponds to a relative frequency distribution. On the left we have a histogram. On the right we have the relative frequency histogram. Notice that they take on the same shape. On the left one we have the columns representing the heights being frequencies, whereas on the right graph we see that the heights of the bars are the relative frequencies or percentages. Take a moment to think about why the shapes are the same. Think back to our examples comparing frequency distribution to a relative frequency distribution. Normal distributions have histograms that are what we call bell-shaped. This agrees with the idea of a normal frequency distribution that we mentioned earlier. The bar heights, which are our frequencies, start low, get bigger to a maximum, and then get smaller again.